Alright, Assalamu alaikum. This is Talha bin Nadeem, and this is the second recorded video lecture of the topic of combustion and combustion chambers. Um, in the before starting today's video, I will briefly go through the uh, topics which we covered in the last recorded video lecture, so that you guys may have some idea about what we were discussing. First of all, we basically started off with the definition of combustion, and I explained you that it is basically the burning of any fuel in the presence of air, and uh, as a result it will give you the oxides of the elements. For example, if I have a methane and I burn it, then I will get carbon dioxide and water vapors. Then we discussed the combustion reactions and their equations, that how these equations are going to form. As I explained earlier, that for example, if I have a fuel methane and I basically combust it, burn it in the presence of air, as a result I will get a molecule of a carbon dioxide and I will get two molecules of water vapors, and in order to balance the chemical equation I will add 2 in the oxygen as well. Then we discuss the calorific values of a fuel, and I explained the difference between the net calorific value and the gross calorific value. Then we started the topic of homogeneous mixtures, and I explained that the homogeneous mixtures are desirable for SI engines, and carburetor is basically that equipment which performs this process of preparing a homogeneous mixture for combustion. And then we also discussed the factor of normal flame velocity, and we also discussed that for the stoichiometric ratio of 1.1 to 1.2 we will get the maximum flame velocities. Then we move forward towards the topic of heterogeneous mixtures, and I explained earlier that uh, that in CI engines we basically we have a heterogeneous mixture because the fuel is being injected after the compression stroke. So and because of the high temperatures of this hot air, the fuel basically gets self-ignite after gaining the energy from the hot molecules of the air. Then we discuss the stages of combustion, and I explained that in SI engines we have basically three stages of combustion. Uh, First one is the ignition lag, second is the propagation of flame, and third one is the afterburning. And this ignition lag, at the beginning of this first period, which is ignition lag, spark ignites, which will basically combust the fuel which is present in the quiescent layer, and then these already burned uh, particles of flue gas will move forward, and it will compress the air fuel mixture which are present in front of the which are present beyond them, and they will transfer the energy to them, and then they will then they will combust. So ignition lag is that duration from where the combustion has started, and we do not have that much significant rise in the pressure. Second period starts when a sudden increment in the pressure occurs, and this second period is basically known as the propagation of flame. So in this phase of the propagation of flame, the flame speed reaches its maximum velocity, and the entire combustion chamber um, and the air-fuel mixture in the entire combustion chamber will start to combust. And after that, in the third phase, that is of the afterburning, most of the fuel particles have already been combusted. It is basically the exhaust stroke. It is basically the power stroke. Now the piston is moving downward. The pressure will start to decrease, and if there are any fuel particles which has still not combusted yet, it will also combust in this phase. So then we discussed about the flame front propagation, and I discussed that it depends upon the two factors. First one is the reaction rate, and the second one is the transportation rate. Then I also explained this graph that in the first region we have low transportation rate, and similarly we have we have a low reaction rate in this region as well. And due to this low reaction rate, the advancement of the flame front is quite slow, and from B to C we have a rapid increment, we have a rapid transfer of a rapid propagation of a flame, because we have a higher turbulency in this region, and this turbulency is present because the flame has now gone beyond the quiescent layer, and in this region the reaction rate is quite high. Similarly, in this region from C to D, the reaction rate is again quite low because we have only few particles of the fuel left, and whenever it gets the oxygen to combust, it will get combust. So the reaction rates from C to D is also quite low. Okay, then we discuss the factors which basically influence the flame speed, and I explained that with the increase in the turbulency, the flame speed will also increase, and it will reduce the tendency towards the knocking as well. Then I explained then the second factor was of the fuel-air ratio, and I explained this graph that the maximum flame speeds occur when the equivalence ratio is from 1.1 to 1.2, and third factor is of the compression ratio. By increasing the compression ratio, pressure and temperatures of the working mixture increases, which will result in the higher flame speed. So the next factor was the temperature and pressure. When we increase it, higher flame speeds are achieved. Then we discussed another factor of the engine output, engine speed, and the engine size. Next, we discussed the phenomena of the knocking in SI engines, and I explained that in SI engine, the knocking basically occurs at the end of the combustion process, because if we divide the air-fuel mixture which is present inside the combustion chamber in layers. For example, this is the layer where the combustion has started. It will compress the next layer, and because of this compression, the temperature and the pressure of the next layer rises. And if that temperature increases the self-ignition temperature, the knocking will appear. A secondary flame will be produced, which will propagate against the direction of the main flame, and because of this, knocking will be produced. So this is the phenomena of knocking in the SI engines, and it usually occurs at the end of the combustion stroke, at the end of a combustion. Here you can see that we have some uh, severe pressure pulses here, which which indicates that we have a knocking in our engine. So now today I am going to start off with the factors which basically affects the knocking. I didn't cover this topic in the last video because of the time duration limit, and that the video duration for that was already gone beyond 75 minutes. So today I am going to start this topic. The first factors are the density factors. So the first one is compression ratio. So as I explained earlier, that when you increase the compression ratio, what we are doing is we are basically increasing the pressure, we are increasing the operating pressure and temperature of the working fluid. So when we increase the temperature and pressure, it will decrease the ignition lag, and when the ignition lag has been decreased in SI engine, it will result in the greater tendency towards knocking. So we can conclude it by saying that if the compression ratio increases, then the knocking will also, then we have a higher tendency towards knocking. The tendency towards knocking has also been increased. Then the next factor is of the mass of inducted charge. It is basically the the mass of the air fuel mixture which is being entered into the combustion chamber for combustion. So we basically control this amount of the mass either by a throttling valve, throttling or butterfly valve, or by a supercharging as well. So what happens if we increase the amount of the air which is going into the combustion chamber? It will reduce the temperature and the density of the charge. So since the working temperatures have been reduced, it will result in the decrease in tendency towards knocking. So we can say that if we reduce reduce the mass which is entering into the combustion chamber, either by throttling or by supercharging, it will decrease the tendency towards the knocking as well. So it also has a direct relation. Okay, next is the inlet temperature of the mixture. As I explained earlier, that when we increase the temperature of the working fluid, so as a result the ignition lag will be reduced and we will have a greater tendency towards the knocking. So if we increase the temperature of the working fluid, it will have a greater tendency towards knocking. So it also has a direct relation as well. Okay, the next factor is again the temperature, but this time the temperature is of the combustion chambers walls. So what will happen here is, again, if we have a hot spots in the combustion chamber, or if the temperature of the combustion chamber is quite high, so it will reduce the ignition lag duration, and it will result in the reduction in the it will increase the probability of the knocking as well. So if we increase the inlet temperature, if we increase the temperature of the combustion chamber walls, so knocking will also be increased. So again, it has a direct relation as well. So next is of the power output. So as I explained earlier, that the power output of an engine is being controlled by the pressure at which your engine is being operating. Uh, so if we are basically reducing the power, means that the operating pressures of the engine has been reduced. Uh, since the operating pressures are reduced, that operating temperatures will also be reduced, and it will result in the reduction in the tendency towards the knocking as well. Means your engine will have a lesser tendency towards knocking. So we can conclude the density factors by saying that all the density factors like compression ratio, mass of inducted charge, inlet temperature of the mixture, temperature of combustion chamber walls, and power output of engine, they all have a direct relation with the knocking. If we increase these parameters, it will have a greater tendency to knock. If we reduce these parameters, it will have a lesser tendency to knock. Now moving forward, next factors is of the time factor. So starting off with the factor of turbulence, as I explained earlier, that when we increase the turbulence, the flame speeds are being increased, and when the flame speeds are being increased, the flame will travel throughout the combustion chamber very quickly, and as a result it will reduce the tendency towards knocking. So when we increase the turbulence in combustion chamber, knocking will be reduced. So here we did not have a direct relation, we have an inverse relation. So by increasing the turbulence, the knocking will be decreased. But we have to keep that in mind, in our mind, that the more turbulence, the higher turbulence can even result in the can also result in extinguishing the flame as well. So combustion chambers are usually designed by keeping that in our mind, that it should not extinguish the flame. It should the turbulence should be that much that it is only increasing the flame speed and not extinguishing the flame. So next factor is of the engine speed. As we increase the engine speed, we basically increases the turbulence, and since the turbulence has been increased, the flame speeds have also increased, and because of this increment in the flame speed, the flame will rapidly propagate throughout the combustion chamber, and it will have a lesser tendency towards knocking. So when we increase the engine speed, we are giving lesser time for the air fuel mixture to stay in the combustion chamber. Therefore, the knocking will be reduced. So again, here it has an inverse relation with the knocking. Now next point is of the flame travel distance. Flame travel distance is that distance which the flame is covering, and it is you can say that approximately about the clearance volume difference, the length between when the piston is at the top dead center and the cylinder head. So the higher this distance, it has the greater tendency towards knocking. If that distance is low, it means that the flame will travel throughout the combustion chamber very quickly, and we do not have a greater tendency towards knocking. So uh, when we decrease the flame travel distance, what will happen towards knocking? The knocking tendency will also decrease, because the flame has to cover very small distance. uh, Flame has to propagate across a very small distance. But if the flame travel distance is quite high, flame has to travel a larger distance, and therefore the tendency towards the knocking will be higher. Okay. Next point is of the engine size. So again, when we increase the engine size, it means that the flame travel distance has increased, because the distance between the piston top dead center and the cylinder head would be higher when we increase the size of the engine, and your flame has to travel a larger distance. Therefore, the knocking tendency would be higher as well. So if we increase the flame size, tendency towards the knock also increases. So it also has a direct relation. Engine size also has a direct relation with the knocking. Okay. Next factor is of the shape of combustion chamber. So again, we can say that if the shape of the combustion chamber is quite compact, and it means that we have a lesser flame travel distances, and the combustion will take a lesser time to propagate throughout the combustion chamber. So those combustion chambers will have a lesser tendency towards knocking. So uh, we can conclude by saying that if the more compact the combustion chambers are, so it has a better anti-knocking tendency, or you can say the knocking will be reduced. So it has an inverse relation. We have a inverse relation here. The more compact the combustion chamber, it means that we have lesser flame travel distance, and it will give you a better tendency towards knocking. It will basically reduce the tendency towards knocking. So next point is of the location of a spark plug. Again, the location of the spark plugs are designed by keeping that in mind, that the flame should travel the minimum amount of the distance, so that the tendency towards the knocking is also very minimum. So minimum, we have to keep that in mind, that minimum, we should have a minimum flame travel. Spark plugs should be placed in such a place that where we can have a minimum flame travel distance. So minimum flame travel distance, the knocking tendency is also minimum. So we can conclude it by saying that turbulence and engine speed have inverse relations, whereas the flame travel distance and engine sizes have direct relation with the knocking. Similarly, when we are talking about the shape of a combustion chamber, the more compact the combustion chamber, the better anti-knocking characteristic it has. And if we have placed a spark plug in such a position where we did not have a minimum flame travel distance, we will have a greater tendency towards knocking, because flame has to travel a larger distance, and it can result in knocking. Okay. next factor is of the composition factor, and this composition factor is basically of the fuel air ratio. So as I explained earlier, that the maximum flame speeds are occurred when the equivalence ratio is from 1.1 to 1.2. So maximum flame speed and flame temperatures occur when we have a equivalence ratio of 1.1 to 1.2. So when this equivalence ratio is 1.1 to 1.2, we basically have we do not only have higher flame temperature, but we also have a higher reaction time as well. So uh, we also have a higher reaction rate as well. So it means that the flame will travel throughout the distance very quickly, since the reaction rates are quite high. So here you can see we have a knock limiting compression ratio and relative fuel air ratio, which is basically equivalence ratio curve for isooctane. And here you can see that for equivalence ratio of about 1 to, let's say, 1.2, and you can see that for isooctane the compression ratio is about 7. So if we are operating our IC engine and our fuel is isooctane, so we cannot operate this IC engine beyond the compression ratio of 7. Otherwise it will give us the knocking, which is undesirable, and it can have a drastic effects on our IC engine. So this is what this graph is explaining here, that for isooctane we can have a maximum compression ratio of 7. We cannot go beyond that, otherwise the knocking will occur in our IC engine. Okay, this is just the summary of what I have explained in the past 15 to 20 minutes, and I expect that you can study this table and relate with the lecture of this video with the past 15 to 20 minutes which I have explained, which I have tried to explain. I will give you the idea that how you are going to study it. For example, if I am increasing the compression ratio, it will result in the increment in the temperature and the pressure. Okay, so the next is what action should be taken. So since the temperature and pressures are increasing, it will result in the higher tendency towards knocking. So we have to reduce the compression ratio. We have to reduce this increment in the temperature and pressure. We have to reduce this temperature pressure, which we have to reduce this compression ratio. So the question is, can we really change the compression ratio? Since the compression ratio is a designing factor, and we cannot control it, therefore the operator cannot control it. Whereas if we are talking about the mass of inducted charge which is entering into the combustion chamber, it will also result in the increment in the pressure. So what action is, and since the increment in the pressure results in greater tendency towards knocking, so what action should be taken? We should reduce the mass of the inducted charge. And the question is, can we control it? So yes, if we can control the amount of the air which is entering into the combustion chamber, we can reduce the amount of a supercharging. We can reduce the amount of air which is going into the combustion chamber, either by throttling valve or a supercharger. So in that case, I have explained these two factors, and I expect that you can relate the past 15-20 minute lecture with and you can study this table by yourself. So now Now I have another topic, and this topic is of the combustion in CI engines. So far we have studied the combustion in SI engine, and not only that, we also studied the knocking phenomena as well. So today, now we are going to start off with the topic of a combustion in CI engines. So in CI engine, as I have explained earlier, as Dr. Usman has explained earlier in his earlier videos, that CI engines are usually operating at a higher compression ratio, and they usually operate at the compression ratio of about 16 to 12. And not only that, and the question is that why are they operating at the higher compression ratio? So the answer to that question is that in CI engines we are only compressing the air, therefore we can compress it up to higher compression ratios, because air is not going to combust itself until the fuel is being injected into it. Whereas in SI engines we are limited to the compression ratios of 7 and 8, and because of and we are limited to this compression ratio because the fuel is already being inducted into the combustion chamber along with the air, and those fuels cannot survive the higher compression ratios. If we enter this air fuel mixture into the engine which is operating at a higher compression ratios, it will result in the knocking, and your engine will not perform efficiently and effectively. Therefore SI engines are restricted towards the lower compression ratio of about 6 to 10, whereas we can operate our CI engines at a higher compression ratio of about 16 to 20. So fuel is being injected, and fuel is being injected by the injection system. I have discussed the details of the injection system in mechanical injection system topics. So and when this jet fuel jet has been sprayed by the fuel nozzle into the inside the combustion chamber, it will move, it will go against the compressed air, against the resistance which is being offered by the compressed air. Therefore the particles which are in the surrounding, or you can say the periphery of this jet, will get dispersed and will get vaporized as well, and will be mixed with the air which is present in the surrounding. Whereas the core of the jet, this core of the jet will penetrate throughout the combustion chamber, so that the air molecules which are present at the bottom layer of the, which are near to the piston, will also get the fuel, and they will also be combusted. So the jet of the fuel disintegrates into a core, and the periphery of the periphery of this jet will be dispersed in the surrounding. So the spray envelope is created both by atomization and vaporization, and we have to keep that in our mind that turbulence in these combustion chamber plays a very vital role in ensuring that the entire fuel, so what the amount of the fuel which we are injecting into the combustion chamber is being combusted, and the turbulence, this turbulence of the air particles will basically, what will happen here is that, for example, this air particle is coming, it will take the fuel vapors along with it because of this turbulence. So therefore this periphery of the jet will get disintegrates. So a mixture of, and as a result we get a mixture of air fuel ratio, and this mixture of air fuel ratios are quite localized, and it will be a heterogeneous mixture because it will not be constant throughout the combustion chamber, and as a result since the temperatures inside the combustion chamber were quite higher than the self-ignition temperatures of the fuel, therefore the combustion will occur at the localized point. And when this burning, when those region where the combustion has occurred, because of as a result of a diffusion, these flue gases, particles of the flue gases will diffuse throughout the combustion chamber and will transfer the heat energy, amount of the heat energy, towards the surrounding fuel molecule, and when that they gain the temperature which is higher than the self-ignition temperature, they will also get combusted. So here the fuel so here the fuel will get combust, initially localized and then throughout the combustion chamber. Means that, for example, if this is our combustion chamber and this is the piston which is at top dead center, for example, at this point the combustion occurs, and at this point the combustion occurs. We have these localized point where the combustion occurs. So what will happen? These flue particles, particles of flue gases, will disperse throughout the combustion chamber, will diffuse throughout the combustion chamber, and it will result in the combustion of the surrounding molecules of the fuel as well. So if the air within the cylinder were motionless, under these conditions there will not be enough oxygen in the burning zone, and burning of the fuel would not be will be either slow or totally fail. So we have to keep this in our mind that turbulence in CI engine is of quite importance. Here I have attached the two figures as well. You can see that this is the region where this is the diagram where we do not have any air swirl, so combustion will occur. But in, let's say, this is the surrounding particles, surrounding air, surrounding air does not get any fuel particles, so it will not combust it. But if we have a air movement, we have a combustion chamber designed like this, that air is moving, blowing towards the fuel, towards the jet of the fuel, it will take away the fuel particles along with it, will get combusted, and the fresh air will come, the new air particle will come, then it will take the further particles along with it and will get combust. So this is how the turbulence, so that's why the turbulence is of the great importance. It will help in propagating the flame throughout the combustion chamber. It will result in increment in the reaction rates as well. So we have to keep this in mind, in our mind as well, that this turbulence should be very controlled. And if we have an uncontrolled combustion, if we have an uncontrolled turbulence, then it will result in the it will not increase the reaction rate, it will not increase the propagation of the flame throughout the combustion chamber, rather it will extinguish the flame. Okay, next we have the topic of the stages of combustion in CI engine. CI engine consists of basically 4 stages. First one is the ignition delay period. Second one is the rapid combustion period, and third one is the controlled combustion period. Means second one was the uncontrolled combustion period, in which the rapid combustion will occur. Third one is the controlled combustion period, whereas the fourth one is the period of after burning. So what will happen here is that you can see that in this graph here you can see that in this region of stage 1, at this point the fuel injection has already been started. The fuel injection start from this point to this point, and during this process there is no combustion. The surrounding temperature inside the combustion chamber doesn't go beyond the self-ignition temperature of the fuel, so there will not be any sort of a combustion. So ignition delay is basically that period from where the injection has started, injection of the fuel has been started, up to that point where the combustion will occur. So this duration is called ignition delay period. Now here you can see, since a lot of fuel particles have already been accumulated inside this combustion chamber, now this combustion will be rapid, and we cannot control this amount of we cannot control this combustion, since the fuel particles are already present inside the combustion chamber. So once they get the temperature which is beyond the self-ignition temperature, they will combust rapidly, and we will achieve the maximum pressure of the cycle at the end of this stage as well. Next stage is of the period of controlled combustion, and here you can see that still the fuel would be injected, and if there are some fuel particles which are present inside the combustion chamber will get combusted. There will not be pressure rise here, since the piston is moving towards the bottom dead center. This stage is called controlled combustion period, because we can control the amount of a combustion here, amount of the fuel which is being injected here. And here you can see that from the start of the stage 1 up till the end of the stage 3, the fuel injection has occurred. Means that fuel would also be injected even after the combustion as well. Means even after achieving the maximum pressure in the cycle, we will still have the fuel which is being injected into the combustion chamber, but we are controlling this amount of the fuel. That is why this stage is called period of controlled combustion. And the next stage is of the period of after burning, and here you can see again the piston is moving downward towards the bottom dead center. So the pressure will decrease, and pressure will be decreased, and you can see that no further combustion in this stage will occur. Okay, so this was the brief introduction regarding the 4 stages. Now we will quickly go through the details as well. This the first stage was of the ignition delay period. This period is also known as the preparatory phase, because in this period the fuel has been started to inject into the combustion chamber, injected into the combustion chamber, and the fuel air mixture will start to form. Therefore this phase is also known as the preparatory phase. So this period is counted from the start of injection to the point where the combustion, from the start of injection to the point where the combustion will start to occur. There is a definite period of inactivity between the time. So by the word inactivity here, it means that we do not have any combustion during this period, and the fuel which is being injected into the combustion chamber will be accumulating inside the combustion chamber. So this is what is happening, and this delay depends upon the this delay from the starting point of injection towards the start of the combustion depends upon the two factor, and the first one is the physical delay and the second one is the chemical delay. So again, this physical delay basically depends upon the atomization and vaporization and also the mixing of the fuel with the air. Means how this fuel will be mixed, atomized and vaporized with the air. This is the physical delay duration, and the greater the physical delay, the greater amount of the fuel would be accumulated inside the combustion chamber, and when it achieves the temperature which is beyond the self-ignition temperature, then it will combust, and greater the amount of a fuel which has been accumulated inside the combustion chamber, the rapid combustion, the rapid increment in the pressure will occur. Next factor was of the chemical delay, and as we know that at the start the combustion will start slowly and then it will start to propagate, it will accelerate throughout the combustion chamber. So this chemical delay is usually larger for the fuels which are being used in the CI engines, and since the temperatures are also high, therefore the fuel will get combusted when they achieve the desired temperature, the self-ignition temperature. So generally the chemical delay is larger. However, it depends upon the temperature of the surrounding, and at higher temperatures the chemical reactions are faster. So if the operating temperatures are higher, the chemical reactions are faster and the physical delay will become longer. Okay, so generally the chemical delay is longer than the physical delay. Means the time for required which is required for the combustion, for the atomization, vaporization and the mixing of the fuel with the air is lower than the rate of a reaction. But when we have a higher temperatures, the reaction rates are quite high. And in such cases the physical delay will become longer. Okay, next stage is of the period of rapid, or you can say uncontrolled combustion. As I mentioned earlier, that in this period, in this phase, what will happen here is that a large amount of the fuel has already been accumulated inside the combustion chamber, and when it achieves the self-ignition temperature, the combustion will start. And here you can see that in the indicator diagram, this is the point, this is the region where the combustion has started, and in the indicator diagram we can see that there is a definite pressure increment up till this point. So this is the point where the rapid combustion will end, and the fuel which has already been accumulated inside the combustion chamber is now combusted. Therefore no further combustion, therefore no further increment in the pressure rise will occur. So in this period pressure rises rapidly. This period is counted from the end of delay period, or we can say either that the end of the delay period or the beginning of the combustion process, to the point where we achieve the maximum pressure of the cycle. The amount of a heat, the rate of the heat which is being released in this period is maximum, and the combustion will depend in the duration of the delay period as well. The longer the delay period, the more rapid the combustion will occur, because the more fuel is already been accumulated inside the combustion chamber. So this is what the period of rapid combustion is. So next is the period of the controlled combustion. As I mentioned, that the fuel which was accumulated inside the combustion chamber has already been burned, and but we have not ended the injection of the fuel. Therefore, the new fuel, more amount of the fuel would be injected, and this fuel will also get combust. No further pressure rise will occur, and here you can see that from point here to here, start of the third process towards the end of the third process, there is no further increment in the pressurization, but there the fuel is still being injected here. Here you can see that injection is from the start of the first stage up to the end of the third stage. Therefore, the fuel is still being injected into the combustion chamber, but this injection of the fuel is controlled. Therefore, this stage of the combustion is called period of controlled combustion. The temperature and pressure in the second stage is already quite high. At the end of the second stage is already quite high. The fuel droplets injected during the second phase burn faster with reduced ignition delay as soon as they find the necessary oxygen, and any further pressure rise is controlled by, so we are basically controlling the further pressure increment by the injection rate, the amount of the fuel which is being injected into the combustion chamber during this stage. So the period of controlled combustion is assumed to end at the maximum cycle temperature. Means that at the end of this stage we will have the maximum temperature of the cycle. Means that at this point we will have the maximum temperature of the cycle. Next and the last stage is of the period of after burning, and since you can see that the fuel the injection of the fuel has also ended here at the ending of the third stage. Therefore, the piston is just now moving towards the bottom dead center, and the pressure in the indicator diagram as well, you can see that the pressure is also dropping. So in case if there is any unburned fuel particle, it will get combust, but no further injection of the fuel will occur in this stage. So the unburned or maybe some partially burned fuel particles may find some oxygen to combust and form the combustion products. This process continues for a certain duration, and this is called after burning. So the period starts from the point of the maximum cycle temperature and continues over the part of the expansion stroke. It may corresponds to 70 to 80 degrees of the crank travel from the top dead center. Here you can see that from this point, let's say this is the 10 degree of crank travel up till this point. Here this is basically the region of after burning. So these are the 4 stages of the CI engines. I hope these stages are clear to you, and all of you must have understand the basic concepts of it. Alright, now I'm going to start off with the topic of the factors which basically affects the delay period. So again, as I mentioned earlier, that this is the first stage of the combustion in CI engines, and this delay period depends upon the many factors, and we will discuss those factors here. And during this delay period, the fuel injection has already been started, but the combustion hasn't started yet, and the point from where the injection of fuel started up to the point where the combustion starts is basically the delay period. Here, if I again show you the indicator diagram, pressure and crank travel indicator diagram, you can see that during the first stage is from the start of injection towards the start of combustion, and the injection will end at the end of the third stage. Now coming back, so this delay period depends upon many factors, and the first and the very important factor is of the compression ratio. So during this factor, we can see that by increasing, as I mentioned earlier, that by increasing the compression ratio, the pressure and the temperatures inside the combustion chamber will be increased. And since that these pressures and temperatures have been increased, therefore it means that fuel will achieve the self-ignition temperature bit earlier. Therefore, when we increase this compression ratio, the delay period will be reduced. We will observe that reduction in the delay period because the higher temperatures have been achieved, and it will help the fuel to get combust as soon as possible. Therefore, we will observe the reduction in the delay period. Similarly, when we are talking about the intake temperature of the air, since the temperature of the air has been increased, therefore as soon as the fuel is injected into the combustion chamber, and the temperatures are very high inside the combustion chamber, so the fuel will combust as soon as it gets in contact with this hot air, because the temperature is beyond the self-ignition temperature of the fuel. So again, when we increase the temperature of the incoming air, we will observe the reduction in the delay period. So again, the compression ratio is also inversely proportional, means that delay period is inversely proportional to compression ratio. Similarly, delay period is inversely proportional to the intake temperature as well. Now in this intake pressures, when we increase the intake pressure, again increasing the intake pressure will result in the increment of the density, and it will also reduce the auto ignition temperature as well. Therefore, when we basically increase the pressure, the ignition delay or delay period, we can call it as ignition delay or delay period, will get reduced, means combustion will occur more quickly because the intake pressure has been increased. Means it is also inversely proportional, knocking is also inversely proportional to intake pressure. So the next is of the quality of the fuel. So we have to use those fuels um, which has basically a lower delay period, or we can say it has a higher cetane number. Cetane numbers, when the cetane numbers are higher cetane number fuels are being used in the CI engines, and higher cetane number means that they will have a lower delay period. Next is of the engine speed. So again, when we increase the engine speed, therefore the engine is reciprocating with in lesser time, we can say, and it is reciprocating, it is taking smaller time while reciprocating, since the speed has been increased. Therefore the delay period will also be reduced, because combustion would be occurring very rapidly. So if we increase the speed, the delay period will also reduce. But when we are talking about the crank angle, it will increase, the delay period will be increased when we are talking about the crank angle. But when we are talking about the time duration, means we are talking about milliseconds, then the reduction will be reduced. Next is of the engine output. So again, if we want to increase the engine output, we have to increase the pressure and operating pressure and the temperatures, and we also have to increase the fuel air ratio. So increment in all of these factors will decrease the delay period. So we can say that increasing the engine output will decrease the delay period. So atomization, next factor is of the atomization and duration of injection. This factor is of quite importance as well, because increase in injection pressures will also reduce the delay period, and because it will, by increasing the injection pressure, the rate of atomization has increased, and since the rate of atomization has been increased, therefore it will take lesser time to combust. So we can say that the delay period will be reduced when we increases the injection pressure. Increment in the injection pressure will result in the better atomization of the fuel, therefore the delay period will be reduced. So next factor is of the injection timing. Injection timing, if we have a advanced injection timing, then it will reduce the delay period. So they were the some factors which on which the delay period depends. And here again you can see this is the table regarding the factors, variables on which the delay period depends. So again, I will not go into the details since I have already discussed these factors. I will help you, I will guide you that how you guys will study this topic, this table. For example, when we are talking about the increment in the variable, and when the cetane number of the fuel has been increased, so what will happen? The improvement in the cetane number will basically reduce the delay period, and the reason is because it will reduce the self ignition temperature of the fuel, and fuel will self ignite itself at the lower temperatures. So the next is the injection pressure. So as I mentioned earlier, that injection pressure here, as I mentioned, that injection pressure will basically
increase the atomization, and because of this increment in atomization, there will be the fuel will take lesser time to self-ignite, and there will be reduction in the delay period. So it reduces the physical delay due to the greater surface to volume ratio, or we can say due to the better atomization because of these higher injection pressure. So this is how you guys will study this table. I am again going to discuss another factor, which is of the jacket water temperature. And when we basically increase the jacket water temperature, what will happen is, here is we are basically increasing the temperature of the combustion chamber, which will ultimately causes the reduction in the delay period. And the reason here is also mentioned, that there is an increment in the wall and air temperature. So this is how you guys can study this table. I have already discussed these factors in quite some details, and I hope you guys can study it by yourself. Okay, next topic is of the comparison of knocking in SI and CI engine. I have explained the knocking phenomena in SI engine in quite some detail, that how the knocking in SI engine occurs. Now I am going to explain about the knocking in the CI engines. So what happens in CI engine is, since the self ignition is occurring from the start of the combustion process, therefore the knocking will be occurring inside the CI. We can conclude by saying that in CI engines there is always a knocking phenomena, but this knocking phenomena should be quite controlled, should be under control, in order to, so that we do not have a drastic effect on our IC engine. And therefore we can say that in SI engines the knocking basically occurs at the end of the combustion process. As I mentioned earlier, that the layers will get compressed, and the last layer, or maybe the second last layer, will basically result in the knocking. But in CI engines there is always a knocking since the start of the combustion process. So we can say that in SI engine knocking occurs nearly at the end of combustion, but in CI engines knocking occurs near the beginning of the combustion process. So this is how the knocking, this is the difference between the knocking, main difference between the knocking in SI engines and CI engines. Here you can see that these pressure pulses are occurring at the end of the combustion process, whereas in CI engines they are occurring at the starting of the combustion process. So in SI engine the charge that auto ignites is homogeneous, but in CI we do not have a proper homogeneous mixture, since the fuel is being injected after the compression. So since in SI the charge is homogeneous, therefore the intensity of the knocking is also quite higher, and therefore the knocking in SI engines is also referred as detonation. I have explained this point in the last video as well, that we have a severe knocking in SI engines since the mixture is homogeneous mixture, and therefore the knocking in SI engines are called detonation. In CI engines only air is compressed during the compression stroke, and ignition can only take place when the fuel is being injected. Thus there can be no pre-ignition in CI engine. In CI engine there is always an audible sound present, since we have a self ignition which is occurring in the combustion, during the combustion. But when this audible sound becomes severe, it causes heavy vibrations in the engine. So we have to make sure that these severe vibrations does not occur in the IC engine, in CI engines. So fuel in these engines is also of quite importance. For SI engines, a fuel must have a good octane number, but if a fuel has a good octane number, it means it has a very high ignition lag. High ignition lag means it will have a low cetane number. Similarly, in CI engines, what we desire is the fuel should have a good cetane number, means it will have a lower ignition lag, but if it has a lower ignition lag, it means it has a lower octane number, and we cannot use this fuel in SI engines. So octane numbers and cetane numbers are inversely proportional to each other. A fuel which has a higher cetane number can be used in CI engines, since it has a lower ignition lag, but in SI engines we require the fuel which should have a higher ignition lag, so we cannot use that fuel. So but if we are talking about a fuel which has a higher ignition lag, it means it has a good octane number, and we can use it in SI engines, but we cannot use it in CI engines since it has a higher ignition lag, and we want low ignition lag in CI engines. So these are some of the characteristics which can reduce the knocking in SI engine and CI engine. So I will discuss these factors. I have already explained these phenomena in quite some detail, but I will quickly go through this table. For example, if we are talking about the ignition temperature of the fuel, in SI engine the ignition temperatures should be higher, but in CI engines the ignition temperatures should be lower. Similarly, when we are talking about the ignition delay, as I explained earlier, in SI engines we basically require a longer ignition delay, but in CI engines we require shorter ignition delay, so that lesser amount of the fuel is accumulated in the combustion chamber, and we do not have that much uncontrolled combustion during the second phase. Next is of the compression ratio. SI engines are restricted to low compression ratios. On the other hand, CI engines can operate at higher compression ratios because only air is being compressed in CI engines. So inlet temperature, again it should have a low inlet temperature, whereas in CI engines we can have a higher inlet temperature as well, because only air is going to be compressed. But if we have a higher air temperature in SI engines, since it is being mixed with the fuel, it may result in the self ignition of the fuel in the air fuel mixture. Therefore we can have a knocking in that case. And similarly, when we increase the pressure, we have basically when we are talking about the inlet pressure, we cannot operate at a higher inlet pressure. We cannot operate our SI engine at higher inlet pressures. However, we can operate our CI engine at higher pressures because we are only compressing the air. Similarly, when we are talking about the combustion chamber walls temperature, it should be low, otherwise the self ignition will occur, knocking will occur. It can be high in CI engines because only air is being compressed. When we are talking about the speed, it should be high, speed should be high, and in CI engines speed should be low. And when we are talking about the cylinder size, SI engines will be operating at a smaller size, and CI engines would operate at larger cylinder sizes. So this was all about the topic of knocking. Now I'm going to start off the topic of the combustion chambers. I will discuss these combustion chambers briefly, not in some quite details. Therefore it will not take that much time, and I will cover this topic in this video as well. So when we are talking about the combustion chambers of SI engines, we have basically different arrangements, different types. The first one is T-head type, and here you can see the shape of this combustion chamber is of the alphabet T, and here you can see at one end we have basically the inlet valve. I represents the inlet valve, and we have the exhaust valve on the other side, and here you can see we have the spark plug. The spark plug is placed in, which is closer to exhaust valve, in order to make sure that only flue gases go by through the exhaust exhaust valve, and not any fresh air fuel mixture goes with it. So distance across the combustion chamber is very long. So in these type of chamber, there is a higher tendency towards knocking, because fuel has to come through inlet valve and then go from throughout this combustion chamber towards the exhaust valve. So there is a it has to cover a lot of distance. Therefore it has a higher tendency towards the knocking. And here you can also see that we have inlet valve at one side and outlet valve at other side. So it will require two camshafts. One would be operating the inlet valves and the other would be operating the exhaust valve. So it is also a disadvantage in this these type of arrangement. Okay, next here you can see that B and C is also the L head type, and here you can see this arrangement is like the alphabet L, and therefore these type of combustion chambers are called L head type. The next one is also in the shape of L as well. Here you can see, but it has a slightly different design, slightly different shape of the head because of this dome. Okay, here you can see that inlet valves and exhaust valves are on the same side, and we have a spark plug which is placed at the center. In this we have inlet valve and the exhaust valve in the same side, and we have a spark plug placed here. So whenever the fresh air fuel mixture comes, it will get combust, and then it will go into the exhaust manifold through the exhaust valve. So it is basically a modification of T-head type, and it will provide two valves on the same side of the cylinder. Therefore it will require only single camshaft. So the disadvantage of the T-head type is being removed in this L-head type arrangement. So with the detachable head, it may be noted that the cylinder head can be removed without disturbing the valve gears, since they are being placed at the bottom, and when we are removing the head, we will not be disturbing the valve gear assembly. They are very easy to lubricate, and the second one is basically Ricardo's turbulent head design. This arrangement has this shape has basically increased the turbulence. So C has some advantage over the L type, simple L type arrangement as shown in the figure B, and therefore the reduction, we will have a reduction in this arrangement, and we will have a higher flame speeds in C in this C figure, L head type of as shown in figure C. Next is basically I head type, or we can say overhead valve type. Here you can see that valves are being placed at the top, and inlet valves and exhaust valves are placed at the top of the head. So both valves are located on the cylinder head. These type of engines are superior to a side valves, L head engines, when we are talking about the higher compression ratio. So they have a less surface to volume ratio, and they have also less flame travel distance, because these distances would be quite small, and they can operate at higher compression ratios as well. So knocking tendency in such engine is very low, and they also have a high volumetric efficiency as well. Next is of the F type, F head type, and here you can see it is basically a mixture, or we can say a compromise between I head and L head type. So exhaust valves are placed on cylinder head, whereas intake valves are designed on cylinder block. These since the exhaust valves and intake valves are placed separately, therefore it will require two camshafts as well, and these camshafts would be driven by the two separate camshaft gears. So this is the advantage of this F head type arrangement. So this was all about we have studied these five different arrangements, 5 different configurations of the combustion chambers in SI engine. Next we have the combustion chambers of CI engines. Again, as I mentioned earlier, that I will not discuss these combustion chambers in quite detail. I will just briefly go through them. So combustion chambers in CI engines can be classified into 2 categories. First one is the direct injection, and the second one is the indirect injection. As the name suggests, in direct injection, what happens is basically the fuel is injected directly into the combustion chamber and it will get combusted. Whereas in indirect injection system, we have basically a pre-combustion chamber. The fuel will get combust there, and then it will be sent into the main combustion chamber. So starting off with the direct injection system, direct injection combustion chamber. This type of combustion chambers are also known as open combustion chambers. In these types of combustion chamber, entire volume of combustion chamber is located in the main cylinder. So as I mentioned earlier, that there is only one cylinder, and that is your main cylinder, and fuel is injected directly into this volume. Some of the types of these direct combustion chambers are shallow depth chamber, hemispherical chamber, cylindrical chamber, and the last is toroidal chambers. Again, you can study these topics in the book. As I mentioned earlier, that I will just briefly go through the basic concept that what the direct injection and the indirect injections are, and you can study it, or at least you can see the figures from the book. So next and the last type of the combustion chamber in CI engine is of the indirect combustion chamber, and as the name suggests, the fuel is not being injected directly into the combustion chamber. In fact, we have the combustion space is being divided into two parts, and one part is the main cylinder and the other part is in the cylinder head, and it is not a main cylinder. So the fuel is usually injected in the cylinder head. Some of the types of these combustion chamber are swelled chamber, pre-combustion chamber, and air cell chamber. Again, I will not go into the details of these combustion chamber. However, you can study it and you can see the figures. You can at least see the figures of these combustion chamber in the book. So that's all regarding the topic of the combustion chamber, combustion and combustion chambers. This ends up with this chapter, and in the next video tutorial we will solve the numericals, some of the numericals of the combustion, and I expect you guys to carefully watch this video, learn the basic concepts, and in case you have any query regarding this topic, just note down your question and ask your questions in the video lecture, or you can ask it in the WhatsApp group or in the Google Classroom as well. Till next video, Allah Hafiz.